So hi, today we will talk about the voltage ripple in buck converter. So just as a review, we have our switch, we have our diode here, and we have the inductance and also the capacitance. Until now, this is our load, right? Those things. So until now, we assumed the output voltage is constant. I mean, yes, it is more or less constant, but you cannot avoid some kind of ripple, in that capacitor. And I think you can imagine if you choose a really small capacitor, or if the load is drawing too much current, then that ripple will change. And today we will going to analyze how to calculate that voltage ripple. So just before getting into equations, let's look at the mechanism, and let's say this is V in, and when we close the switch, okay, when we close the switch and we are charging that inductor, and if inductor current basically goes over some certain value, so it is both supplying the load and also it is charging your capacitor. So you are slightly increasing the voltage level in the capacitor. Then what you are doing is you are closing that switch. Then you don't have any power flow from your input. So your inductor and capacitor during off time of the switch, your inductor and your capacitor needs to supply the load. Then the inductor current starts decreasing. It is still carrying in that way, but after some time that inductor value will drop, and I will show you the figures. Then your capacitor is going to charge, is going to supply your load. And actually that is more dramatic for the discontinuous conduction mode. If your inductor gets into discontinuous conduction mode, then you don't have any current flowing from the left hand side, so your capacitor needs to supply the just by itself needs to supply the resistance during that time. But today let's do the analysis for continuous conduction mode. Again, I think if you remember and if you reviewed our previous videos, so you will see the inductor current will have that kind of charging time for dTs, and it is discharging for 1 minus d ts. Okay, so and we will have a look at how that characteristics can be linked with the voltage, capacitor voltage. Okay, so here you see a detailed graph of the previous inductor current. So again, this is our zero line, and it starts with non-zero, so it's in the continuous conduction mode, and it is charging. So and it's charging for again that is dTs, and then it is discharging, and since it is at the steady state, they have to come up to the same point, and that area that period is 1 minus d times ts. Right, so again that is our inductor current, and I can assume in the long run, if it is at the steady state, even if you have some peak coming from here, that capacitor voltage is going to stay constant. So that means the amount of current getting into the capacitor and the amount of current going out of the capacitor needs to be same. Remember, the voltage seconds balance in inductor, we have the current seconds balance in capacitor. So otherwise, if they are not equal to each other, your capacitor voltage will climb up or discharge completely. But if it is at the steady state, they need to be equal. So that gives us that relation. If you have some kind of ripple voltage, so let's call that one the load voltage. Let me change it. This is the inductor voltage. Let's call that one I load voltage. Okay, so the load voltage here is going to be the average value of that one, right? So this will be in average going to our load, and the blue one is our inductor current. So of course, there's a ripple in that inductor. So let's go on to our graph. So we have the output current. Okay, this is the average output current. Okay, so now let me just draw just 3 branches. So here I have that current going in average. Okay, again, there's a trick here. Normally we are trying to find the ripple in that capacitor voltage, but this is just a few % of the capacitor voltage, so it will not be dramatic in a properly designed converter. So again, for current, you can suggest, if there's a resistive load and if there's some ripple here, yes, that ripple will directly reflect in the I/O, but we ignore that secondary effect, otherwise it will be like a second order differential equation, and of course it can be solved, and you can see that those effects in your computer simulations. But for us, let's assume that ripple is small, so for current we don't take into account of that effect, and we can assume that current going through that resistance is like somehow DC. Okay, so this is the DC, and then we have the inductor current coming in. So you can see whenever that current is larger than the output current, okay, it will charge our capacitor, and whenever it is, for example here, whenever our inductor current is smaller than the required output current, now our capacitor will supply some current. So again, in the steady state, so that voltage is going to stay constant, so the amount of current or charge getting in and the amount of charge getting out from the capacitor will be constant. So here, let me show it here. So during that time, okay, your C is charging, okay, and during that area, okay, during that time C is discharging. So the analysis technique is straightforward. So if this is current, and I know if you take the integral of IC over some time, it will give you some charge, the amount of total stored charge. So the area here is the amount of charge in columns sent to the capacitor. So again, I can divide it by the capacitance to calculate the delta V. So this is our main analysis. So here you see again it is kind of exaggerated, of course. In a properly designed buck converter you will not see that amount of ripple voltage. But anyway, so let's see the relation before getting into the mechanical derivations. So whenever you reach that point, so at that point your inductor current is equal to your output current, so there is no change in the capacitor voltage, and it is like at the minimum point. Then you just keep charging up, so you are charging up, and at that maximum point you reach the maximum rate of change of the capacitor, but it is still going up. So it's going up and up, and then the amount of charge going up, going down, so there's a tendency to reach a horizontal maximum. So at that point you reach the maximum capacitor voltage, because that is the total amount of charge being sent to capacitor. So you can calculate the ripple voltage delta VC or delta VO using those figures. I think if you are happy with that graph, the rest is just straightforward calculations. But before on, just use some geometry and let's define those things. So if this is our average output current, and again let me plot here, so that all area is delta IL, the total ripple current, which we can calculate using the voltage equations. And again, if you are just taking average, so it will be half of that ripple. Okay, and again, let's draw a line here, and let's draw a line here. So you can see that area is same with that one, that line have the same length with that one, that line has the same length with the other one, and the same thing is here and here, because of these triangles. So what you can say, if from here to here, if this is dTs, oh sorry, not dTs, it will be just Ts. Okay, if this is Ts, you can say from that instant to that instant, okay, this is Ts over 2. So this is Ts over 2. So you can see half of the period the capacitor will be charging, and half of the time it will be discharging. And again, this is regardless of the duty cycle. Here duty cycle is not 0.5, maybe, so I don't know, 0.8, and this is 0.2. But since we are taking the average and from the areas of those triangles, the capacitor will be charging half of the time and discharging other half of the time. Okay, so now how we can calculate that area? I want to find delta Q, and from delta Q I want to find the ripple output voltage. So it is simple. Let's do the calculation. So okay, we want to find delta Q. So how can we find delta Q? So delta Q is that area, as you can see. So I mean, if you can get that rectangular area, so that area is half of that thing. So delta Q can be written as that one times that one divided by 2. So let's write that one. So delta Q is equal to what was it? Delta IL over 2 times, and that one Ts over 2, and again this was the area of the rectangular. I need to get the area of the triangle, half of that one, so divided by 2. So that one is equal to Ts times delta IL divided by 8. Okay, cool. And I know, of course, delta VO, okay, output capacitance is equal to the amount of charge divided by capacitance. So I can write delta VO is equal to that one Ts times delta IL divided by 8C, right? Then I want to get rid of that term, and actually that can be written using the voltage equations. So let's go up. So either you can calculate it from inductor voltage over that area or that area, and here the inductor voltage is Vd minus Vo, and here it is minus Vo. Right, let's write it in terms of Vo. I mean, then it will be easier to take a relation between Vo and delta Vo. So I can write, using right here, using off time. In other words, 1 minus d period. Okay, so delta IL is equal to Vo, okay, times 1 minus d Ts. Right, so let me get rid of myself. So that thing now can be put into this equation. So let's try to put that one. Delta VO is equal to Ts times VO 1 minus d Ts divided by sorry, there need to be an inductance here. I mean, that is coming from the fact that IL is equal 1 over L V dt, VL dt, and you can just write that equation. There needs to be an L, and it becomes 8 LC, right? So here, you can write it, and there's like 2 square, and actually let's write the ripple as a function of output voltage, and in the most of the time, having, let's say, 2 volts ripple voltage, again, having like 2 volts ripple voltage can be insignificant if you have 1000 volts output, but having 2 voltage ripple, is not acceptable if you have a 5 voltage output. So basically, the standard term is the ripple voltage is given as a percentage of your output voltage. So let's do the same here. So I can write delta VO divided by VO as a percentage or as a ratio of that one. So it is 1 minus D TS square divided by 8L C. Right. So now let's go over those equations. So we have that one, we derive that one. So at the end of the day, I have that equation. So the ratio of the ripple voltage as a function of the output voltage can be written like that. So let's talk about a little about that equation. So obviously, if you want a small ripple, what you can do is you can increase the size of the capacitor or the size of the inductor, which is obvious. You can use a larger filter, and your capacitance will have, or the inductance will have, a higher capacity, so the output voltage will not change at all. But of course, that thing, reducing voltage by increasing the size of the inductance and capacitor, will increase your cost and also your size of the converter. And secondly, similar to that one, TS, and again TS is, remember, 1 over Fs, and Fs was the switching frequency, right? So again, similar to that one, again you can increase the switching frequency or reduce TS to reduce the ripple, okay? And you don't have to increase the size of your LS. So if you want to reduce the ripple and keep the converter size small, the best thing that you can do is to increase the switching frequency. But of course, there's a disadvantage there. I mean, first of all, increasing switching frequency will increase your switching losses, both in your MOSFET or your main switch and in your diode. And secondly, there can be, even if you can thermally cool it down, and there may be some problem with the turn on and turn off times, and there's a certain maximum limit, switching frequency limit, that you can achieve with that device. Or again, you can use a much higher switching frequency devices, and they also increase the cost. But again, if you can manage to dissipate the heat, you can get a smaller converter size. And the other factor is 1 minus D. Okay, so 1 minus D has an effect on ripple voltage. So duty cycle has inversely proportional with that one. So let's consider 2 cases where, let's say, D is equal to 0.1 and this D is equal to 0.9. Okay, so in that one, our ripple voltage will be small, and in that one our ripple voltage will be high, and there's a simple relation. And if you look at your switching instance, so that will be something like that. So during this time, okay, so during this time you are getting power from source. So you are just getting power from source during the switch is on, so there's some current flowing through inductor. But rest of the time, all those instants, so your L and C are supplying the load. So obviously you can see if there is a long time, so L and C will be keep discharging and discharging, so that will increase your ripple value. However, if on the other case maybe you have a long time, let's keep them synchronized or something like that. So for all this time, okay, so you are having power from source, okay, and it is just that instant where L and C are supplying the load. So you can see here again, even if the switching frequency is same, so the amount of time that needs to supply the load through the charges in inductor and capacitors are reduced, so you have less ripple. I mean, the of course obvious one is to have a duty cycle of 1. If you have a duty cycle of 1, so the source will be directly connected to your output, so the output voltage will be equal to input voltage and there will be no ripple, okay, as you can see here. Anyway, but depending on some applications, of course the duty cycle is not constant. Your input voltage can be changing and you want to keep output voltage constant, or even if the input voltage is constant, maybe you want to have some adjustable output voltage. And when considering voltage ripple limitations, you need to think about the worst case for that calculation. Anyway, so let's move on with that equation, and actually there's a better representation for that one, so let's try to put it in a much nicer form. So for that, I mean, we discussed Ts is equal to 1 over Fs, switching frequency. Yeah, right. So what is LC? How can you write LC in terms of the switching frequency or in terms of time? So actually, if you remember, so there's a time constant of LC, and actually corner frequency, okay, of the filter. I've showed you the body plots, so transfer functions of those equations. So there's a corner frequency where you start having some negative gain. So that one was equal to 2p square root LC. Okay, so that was the corner frequency, or you can write omega c is equal to 1 over square LC. Right. So how can I write that one? So you can use that equation, and LC can be written as 1 over 4p square fc square, right? And you can use that equation and that equation to here, and let's rewrite those equations. So this is 1 minus d, okay, fs square divided by 8 times 4 pi square times fc square, right? I think, sorry, I made a mistake. I think this should be somewhere here. So let's put that equation to here. So we will have delta VO divided by VO 1 minus D. Okay, this is 1 over Fs square comes here. We have 8. In terms of LC, I will write that one. This is 1 over 4 pi square Fc square, so it will go up. So 4 pi square Fc square. That one and that one cancel each other, so let's write that one. So 1 minus D, we have some pi square divided by 2 times, I think that is the important part here, Fs square. So at the end of day, I mean, if you just look from a signal point of view, okay, this is constant, you know, that is about the duty cycle, but that one is really important. So at the end of the day, the ripple is directly related to the ratio of your corner frequency and your switching frequency. So you want to, if you want a small ripple, you want to reduce that relation. Either you can increase the switching frequency, or you can actually reduce the corner frequency. So for example, let's say this is LC characteristics, so you can have, you know, this is FC, and you want to move that thing, I don't know, somewhere here, let's say FC2. Okay, so if you can reduce your corner frequency of the filter, then you can have a small ripple voltage. And of course, you know, we discussed it in the previous slides, you know, filtering lower harmonics is more difficult than filtering higher harmonics. So that is why, in order to reduce that one, and you can see it from here, you know, L and C size needs to be increased, and that implies having a larger inductance and capacitance. Okay, so again, you know, that is our equation. Okay, so finally, let's talk about the effect of ECR, and you will see those things in data sheets. And ECR is equivalent, okay, equivalent series resistance. This is ECR. And again, you know, we will not cover it for now, but you will see ECL, okay, and this is equivalent series inductance. So depending on the capacitor types, actually, you know, ECR can be quite important. And ECR, you know, is, yes, you assume you are having a capacitor, okay, but again, you know, that capacitor is never an ideal capacitor. You have a small resistance, okay, resistance, and this is our, you know, ECR. And in some cases you can have small inductance. This is your ECL. Again, this is not external components. This is, you know, the internal resistance and internal inductance of a capacitor. And, you know, in an ideal case we ignore those things, but in practical applications that can be quite important. And especially, you know, ECR has a direct effect on your ripples. Again, we did the previous calculations assuming an ideal capacitor. Okay, so here the idea is, yes, we calculated the ripple voltage delta IC, okay, depending on that one, and you can calculate the charge, okay, and that charge is equal to, you know, voltage is related to your voltage and capacitance values, okay. But on top of that, whenever there is some current, flowing your capacitance, if there is an ECR value, okay, if there is an ECR value, you will have another ripple voltage due to that current, okay. And we are not going to analyze it. Again, in the book you can find some derivations, but there are some practical considerations. And in the, sorry about those ones, so in the long run, or in really high frequencies, you will see, you know, that is the, you know, the total amount of ripple current. So again, let me try to plot it. So again, you know, this was our inductor current, so this is IL. So that amount of, you know, that charge and that amount of current is getting into the capacitance to charge it, and that amount of current will create some voltage over that one, okay. So, and you know, all that ripple, you know, delta IL, you know, will create some ripple voltage on the capacitor. And most of the time you will see, you know, that thing is more dominant than that term. So if you, again, if your currents are higher, or if you are working at high inductor ripple currents, then that term will be more dominant than the capacitance itself. So again, let's discuss about a few practical applications. For first of all, in some cases, I am sure you have seen, let's say you have some bus, and in practical PCB boards you see many capacitors connected in parallel, right? And actually, let me show you one with the previous slides. Probably it's quite high. So for example here, so here you see tens of, I think these are ceramic capacitors, and they have many, they are connected in parallel, and probably here, I don't know, but probably they are connected in parallel. So it is, I think here, I think that is the main capacitor, and there are like a couple of capacitors connected in parallel. You will see those things quite a lot, and the reason for that, if you think about it, let me go back. So again, those things can have some resistive components, and actually when you are connecting like that, you are parallel connecting capacitors. So let's say C1, C3, and C equivalent will be C1 plus C2 plus C3, but your ESR value, actually the capacitance, divided by 3, or you can think the current is being divided by 3. So you are making a better capacitor. You are reducing the effect of ESR. The same thing holds with the ESL value. And I don't know, and again you can think of like connecting capacitors in series. Again, it's not a good practice, but sometimes you have to do it to increase the voltage rating of your capacitors. But there are two things you need to be careful. So even if those capacitances are equal, again you can say when you connect them in parallel, the equivalent capacitance will be half, but at least you have the double of the voltage. So again, if the maximum voltage rating of a capacitor is smaller than the voltage values you need to connect, you can connect those in series. But again, like that, you shouldn't assume they will share the voltage equally. Okay, the voltage sharing problem between capacitances can be a big problem, and in sometimes they connect as some parallel large resistances, or as a damping resistor, or in some cases there are some active charge control circuits. But anyway, so if you have the resistances, ESR resistances here, so here ESR, now you see it is twice of R. So it actually gets worse even if you increase the the voltage rating and you are reducing the capacitance. And once you have two capacitors in series, you have twice the effect of the ESR, and it will make your ripple worse. So it is usually much better if you have enough capacitance to connect 2 or 3 or even more capacitances in parallel. So instead of using a single, I don't know, 20 microfarad capacitor, maybe it is better to use 2 10 microfarad capacitors in parallel. Okay.